exciting homework problem, um, which is about this problem that we talked about the last time, that in the sample complexity bounds, we should have this cubic dependence on the horizon, and how this comes about. And I had this hand-wavy argument, like the last time we were talking about, oh, you can improve it to cubic but not beyond. And I had the hand-wavy argument that argued that, oh, you have this Bernoullis, and then no one can do better than this and that. And then I told you that maybe you will have some surprise homework problem where you can actually look at this. And so that's what I did. I wrote it up as a homework problem. So now you can enjoy it. You can prove the lower bound that no one can do better than cubic dependence on the horizon. No algorithm can do better than that. And I think it's a very nice argument. And it is actually just following this very intuitive argument, just making it like more precise in every step. So it's really nice, I think, because it's just like, if you follow the back of the envelope calculations, they happen to be correct, and then it's not too hard to show. Once you know the proof technique, then you can apply it to other things as well. So that was the cubic dependence, but then we saw that that's not enough. It could be much worse. Already in a tabular case, we can see some exponential blow up. So we saw this lower bound that was saying, well, where is it? Well, I never stated it, I guess. It's stating that, yeah, it's here, that the number of trajectories that you need to be able to discover what's a good policy can be exponential in the horizon. It can be 8 to the power of h, even if you choose, like, it doesn't matter what behavior policy you choose, you can always find an MDP such that in that MDP, that behavior policy is just a terrible choice. It's just a bad choice. And so good luck for us trying to do off-policy learning or batch optimization. This exponential complexity hits us hard. But today I want to start with a more optimistic point. Just to see whether we can do anything with algorithms and like what algorithms to use. So batch RL, still, that's the name of the game. What's the date today? March 23rd. And the question to ask is, okay, fine, like maybe we're gonna get bad bounds, but can we adapt or adopt or planning algorithms? The featureized ones. So for the tabular case, we saw that things are bad enough, but maybe if you assume features and then this high compressibility happens, then maybe good things are going to happen. Of course, you can suspect that that's not the case, because maybe the features are just going to be trivial, and then you're back to the tabular case. So nothing really fancy can happen. But maybe you can be lucky in some other ways, and like things are not going to be that bad. So why don't we just start with some planning algorithm and then try to change it so that we can use it for the batch setting. So can we go from planning to batch. So what algorithms did we look at for planning? Give me some algorithm names for the case when you have these features to represent value functions. API, FQI, okay. Right, so FQI is a special case of API. So that these are policy iteration type of algorithms. Right, what else? There was a homework problem. Yes, approximate value iteration, or AVI. And of course, you can do the least squares version of it. Maybe this FQI, this is fitted Q iteration. It can also be called least squares. I don't know. LSPI, policy iteration. These guys have so many different names. But which algorithm wins at the end? Which has the best dependence on the blow-up factor of the approximate? Yay, Polytech. Okay, so that's a policy iteration algorithm. So maybe we should look at Polytech as a promising candidate that maybe you can use it for the batch setting. So how does Polytech work? There is RL theory. Planning. From API to Polytech. Okay, so Polytech was this simple algorithm. Well, all of these algorithms are relatively simple, that runs a softened version of policy iteration. So there is this equation on the top that tells you that the next policy is obtained by exponentating an action value function, which is just sum of previous action value functions. And any of those action value functions is estimated using least squares. Okay, so that's like this last equation here. The Q head of J is just, okay, it's a projected version of the least squares estimate of the action value function of the J's policy. And the way we were doing that in planning is that we said that, oh, why don't we assume that we're lucky and someone gives us this core set for the features. And in this core set, you have these state action pairs. There are not too many of them. And you just run rollouts of this policy and generate returns, and then run many rollouts, take averages. That gives you high accuracy estimate of the return at the core states, or the value at the core states, and then you just do a least squares fit. And the least squares fit, because you start with core states, allows you to extrapolate to other state action pairs without blowing up the error too much. So what do we need to change if we want to run Polytech? which part of this is not going to work. And right now we're in the bad setting. Yeah, we won't have core states. Even if we had core states, what would you do with the core states? So maybe we do have core states, but what do we do with them? We have, like, what's the best setting? We just have this maybe trajectories from some behavior policy that was generating some data through this MDP. Maybe the data is collected in the form of just like it's chopped up into these elementary pieces of like state action, reward, next state, and then you have many of these. Like there are these two settings. So what are we going to do with this? What can we do? Well, we still would need to evaluate a policy, right? So if we want to run Polytech, somehow we need to be able to evaluate the policies. And so in a way, Polytech and these algorithms work as long as you can control the error of approximating the action value function of the policies that you encounter. And so the core task happens to be to evaluate the policies. So if you want to run any of these algorithms, actually, well, okay, some of them are repeats, then the core element is evaluating policies. And in such a way that you can control the L infinity error, the max norm error. So you have a policy, and you have your features. Your feature map maybe maps the state action pairs to RD, and maybe you have your data. Well, okay, maybe first comes the reward. Where certainly it should be the case that the next state in the data comes from the MDP is probably the kernel, and the reward has the correct mean, right? Like, I don't know, at minimum it has to be the case that this holds. Oh, wait, so this is RD. Okay, so we face this problem with policy evaluation based on finite amount of data. And here, it could be that these quadratlets are just pieces of a long trajectory, and so Si prime is really Si plus 1. So you just have one long trajectory in the MDP, and then you chopped it up into small pieces. Or it could be that somehow these are independently generated, which is better. Which one would be better? To have long trajectories, or just to have some coverage? Mix? Yeah, maybe. Well, it turns out it doesn't matter that much. All of them are pretty doomed. So just give me some ideas. How should we go about coming up with Q pi? So Q pi is this, the return. So Q pi SA is the expected return let's say we are a discounted setting. If you're starting from SA and then you're following policy pi. What would you do? You're designing the algorithm. Okay, so let's do impedance sampling. So what is impedance sampling and why is it relevant? Maybe the simplest way to explain that would be to say that, well, this is nothing but nothing else but a big integral of like there is this trajectory-based return, and then you're taking the integral of this trajectory-based return based on the distribution of interest that you obtain. Oh, sorry, that's a tau. So those are trajectories. That you obtain by following your policy pi. And okay, so one simple setting is when the data is actually generated by following some other policy. Let's call it the behavior policy, or just pi of b. And this starts with, I don't know, like the S naught in this case would be sampled from some distribution, which is maybe fully supported on the state space. And then the A naught would be sampled from the whatever distribution is assigned to state S naught by the behavior policy. And then S1 would follow the distribution of the underlying MDP, and so on and so forth. Maybe for simplicity, let's just assume that the rewards are deterministic, so we don't have to write anything about the rewards. And then this continues this way. So clearly, this behavior policy together with mu induces some other distribution. It induces this distribution, this other distribution over the trajectories. And so we have q pi SA. This is just this big integral. So trajectory here would be just, I don't know, like this infinite sequence of state action pairs. And then, you know, this function, maybe this should be a lowercase function. It's just like the return along a trajectory. So the R tau would be just the sum of the discounted return along the trajectory, right? So here implicitly it's understood that tau is like this specific sequence of S0, A0, S1, A1, and so on so forth. So R tau can be written as a function of S0, A0, S1, A1, and so on so forth. Okay. This is lowercase then. So then we have this, and what you can do is that you can do a change of measure. So you can calculate the density of one measure with respect to another measure. So it's called a change of measure. So we asked the question, okay, how dense is this density of that was induced, that would be induced by pi? Oops, sorry. Compared to the density, okay, so how dense is the distribution induced by pi compared to the distribution that's induced by the behavior policy? Right? So that's like the density ratio. And if you knew this ratio, then you can write everything in terms of a big integral with respect to just the distribution induced by the behavior policy, which is nice because you have data from the behavior policy. And so maybe if you have multiple trajectories, then that's a lucky case. If you only have one trajectory, then it's like, ouch, that's not so great. But if you had tau 1, tau 2, tau n sampled from this distribution generated by the behavior policy, so that's like this kind of sampling, then you could say that, well, q of pi SA is expected to be close to 1 over n times, and let's just replace this integral with an empirical mean, where we are plugging in all these trajectories, and then here we just use this densities along the trajectory. And we know that the mean of this is this. So this is an unbiased estimate. As long as we can control this mysterious term here, which is the density ratio, then we should be fine. Because then, I don't know, Hövding's inequality, central limit term, you call it, right? Like if you have nice, so you have this independent, so this is an IRE sequence. If you have independent random variables, which are identically distributed with the correct mean, then the empirical mean is going to converge in all senses to the common mean, as long as the tail behavior of the individual random variables is nicely controlled. For example, if they are bounded. Of course, for weaker convergence, you don't even need bondedness. You sufficient to have just existing first moments. Then the law of large numbers is going to apply. But then you might suspect that maybe my tails are going to be really large, and like I'm not going to get a very nice convergence. And if I ever wanted to have some confidence intervals, I would be in trouble. So usually you want to control the tail. We see here that in order to know whether you can control the tail, you need to know how well you can control these density ratios. And so you have your behavior policy, and then there is the other policy that generates well, there is the policy that you need to avoid. And if you had a trajectory of a finite length, then everything is super simple, right? So if the trajectory would be cut, so it's like this is the cutted trajectory. So cut trajectories. And then maybe we have seen that you can truncate these things because the gamma term becomes really small. So don't worry about like leaving out some terms. So let's just cut the trajectories after, I don't know, 8 steps. So then what, like then we can write the actual probability assigned to these trajectories, right? So the probability assigned to this trajectory under the behavior policy when you're starting from mu is what? It's like it is a big product, right? And then P A naught, S naught, S1. And I don't know, don't like to write that much. Just write the last term. Okay. So what's the probability assigned to pi, to the trajectory, if you follow pi from SA? Well, first of all, this is an all or nothing for S naught. Either S naught is equal to S, and then you get a 1 jackpot, or you get a 0. Same for A naught. And then, okay, I wish I wrote one more term. And then there is this transition probability. Oh, yeah, was this? Yeah, this is correct. Okay. And so then this ratio that is written in this mysterious way, in this discrete case, it just becomes the ratio of these two terms. So that's how it works. The other way around. SA pi all right, so I need to take the ratio of these two guys. So the beginning starts in this way. Oh, don't leave out mu of S naught. And then it's really nice. These guys cancel. Yay. That's really good because we have no idea about what the transition kernel is, because this MDP is not known. So that's really great. And so all of those terms cancel. So here, the rest of the trajectory, you have alternating terms, which are like transition kernel term, policy term, transition kernel term, policy term. The transition kernel terms all match up. They all cancel. The policy terms don't. And so you get this big product from 1 to h-1 of these ratios of what are the probabilities assigned to the actions in the trajectory at the states visited by the behavior policy versus the target policy, the policy that needs to be evaluated. And right, so the good news is that we can compute this. The bad news is that most of the times, this is going to be a tiny, 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 tiny value. It's because the bearer policy is not going to want to take the actions that the target policy wants to take. So there you face this alignment problem. So P and P back not aligned. So then these the weights are going to be very, very small. Most of the time. And because of this, but you will see that, well, first of all, if you had a policy which is not stochastic and it ever takes an action that the behavior policy didn't take, you're out of luck. This weight is going to be 0. It's really harsh. And so most of the time, this is going to have a tiny value. On expectation, this value though is 1. So you have all these terms, the product of lots of terms. Their expectation is 1. And so what happens is that these terms most of the time are really close to 0, and occasionally, because the expectation has to be 1, they gotta be pretty large. But that's gonna be very, very rare. So if you run a simulation and you would look at like how these weights behave in a simulation, unless you're very carefully trying to align these policies, you will see that nothing really happens. And simply this is because, of course, with high probability, the action that is in the trajectory is the action that is generated by the behavior policy. So this value tends to be larger than this value. and therefore you're dividing a small value with a bigger value. All the values tend to be smaller than 1. So then like, it's gonna be mostly just like very, very tiny values. So this is what's called garbage in, garbage out. It's a very rare event. Okay, so there's some relationship to rare event estimation. It's a very rare event that these trajectories are going to be so that like these values are not tiny. So this is just, okay, you can try to run it. It's gonna be, in general, you can try to bound the sample complexity and all that. It's gonna be exponentially bad as a function of the length of the trajectories. And then, of course, the trajectory length, this age, wherever we're truncating, needs to be kept large if you're shooting for some target accuracy. Has to be like the effective horizon, or the bias is going to be large. So this is just not a great procedure. So what else can be done? There is a simple looking remedy, which is not impedance sampling. So this was called impedance sampling. It's like, what is being sampled? It's impedance reweighting in a way, right? Like if we introduce these weights, these W's, and they are reweighting the data, is data reweighting. So there is a weighted impedance sampling version of it, also called self-normalized impedance sampling, and then whatever, plenty of other names exist. So this has somewhat better properties, but it can't do miracles. So the idea is to calculate this ratio. So the idea is that, well, in the long run, so it's hard to see that this is going to buy you anything, but it actually does buy you a little bit in this setting. The argument usually is that, oh, in the long run, this is not much worse than impedance sampling, but that doesn't quite explain why would you want to do this. The reason you want to do this is because it leads to somehow more balanced reweighting of the sample. So you have these normalized weights that sum to 1. And somehow this is a more stable way of estimating the same quantity. This is going to be biased, but I wouldn't worry that much about the bias. The bias goes away at the rate of 1/n. The variance still, which can be quite problematic. But in general, the variance of this weighted impedance sampling version is smaller than for impedance sampling. So what else can we do? This is still not very great. So there are some other tricks with impedance sampling. So basically, you have this sum. So we simplified everything by writing first this sum, and that this sum is inside this other sum in a way, right? Like there is this sum over the independently sampled trajectories. And well, the expectation commutes with the sum, right? So if we move the expectation here inside, then we can realize that, oh, for every time step, we need to know the expected reward for that time step. And then we can do per time step importance sampling. And you can work out the math that is a little bit better, still not going to do miracles. But if you have no better idea, then this is one way of going about things. If your gamma is not too close to 1, so your effective horizon is pretty short, this is okay, like 5 steps or whatnot. Like, that's fine. If it's 100 steps, then it's like, it's gonna be pretty bad. And this way you can create these targets. So you have independently sample trajectories, and then you can run least squares on the top of it. So you could use impedance sampling, create targets, plus apply least squares. Regression on value targets that you created. So that kind of mimics what we were doing, except that we don't have a core set. So these trajectories are started from this distribution mu, not from a core set. And we know what can happen. If you're not starting from a core set, then your extrapolation error can go arbitrarily bad. If your feature matrix is not well conditioned, so to control the extrapolation error, what had to be controlled is this quantity. Is Z is in SA, and we needed to control this phi of Z, its norm, in this moment matrix, where the moment matrix was this weighted moment, so weighted moment matrix, where Z was just going through the core sets. So now you have some data. Maybe you have Z1 to Zn from some distribution over the state action pairs. This is a different distribution than before. And then you can try to come up with a G, which would be maybe unweighted, just the sample mean. This is the empirical variation of the moment matrix. And you can run least squares, and you need to control this term. So we would still, for controlling the extrapolation errors, we would need to control this. And for sure, this can be controlled if the minimum eigenvalue of G is nice. So if the minimum eigenvalue of G is some positive quantity, well, we can always upper bound this by, for any Z, we can upper bound this by the 2 norm of this times the minimum eigenvalue. Right, okay, so square it times the minimum eigenvalue of G inverse. And then you can take the max over of the state action pairs. So that's just because if you have a positive semi-definite matrix, then lambda max, the maximum eigenvalue of this matrix times the 2 norm squared, is an upper bound on this quadratic form, and the maximum eigenvalue of A inverse or B inverse or G inverse or whatever, let's say G inverse, is the minimum eigenvalue of G inverse. So that kind of call it. So if you want to be lucky and you want to control the extrapolation errors, you better control the minimum eigenvalue. And okay, so this is your G hat. That's a random matrix. And so if I want to be nice, then I will say that, okay, let's control the minimum eigenvalue of the population version of this matrix. Because this Z1, Zn follow this mu distribution, so in the limit G hat converges to this other matrix, this let's call it, I don't know, G of mu. So G of rho was the same, right? So that makes a lot of sense. So if the minimum eigenvalue is nicely bounded away from 0, you're good. If not, then bad things can happen. And so there are results that you can write such that, okay, if the minimum eigenvalue is controlled and a lot of other things are happening, then everything can be kept under control. If everything's good, then everything's good. But of course, we know that the worst case, like none of this happens, and no procedure can do a good job at these things. Well, do we know that? Not yet, but we already have some evidence from this lower bound that was exponential in the planning horizon that said that at least for policy optimization, things can be really bad in the bad setting if you're following trajectories. All right. So this is if you follow trajectories and then you try to use least squares, follow policies to get trajectories, try to use least squares. What else could be done? In what other way can we estimate Q of pi? TD method, yeah, find this saying. Right. And so we don't have to go, like TD is usually written as this incremental algorithm that keeps updating the weights and whatnot. But it is really based on the idea of somehow setting, like finding some parameter that kind of like is just a nice parameter that's derived from basically the Bamel equation, right? Like TD is just like saying, oh, Q pi is the fixed point of the policy evaluation operator. Oh, yay. So TD. Q pi is the fixed point. All right, so then we can just plug in if Q pi is equal to, you know, some linear function of the features, then maybe this equation should be satisfied. Right? So here you have the equations. Sorry, you have the unknowns. And this equality is for S times A dimensional vectors. There are SA constraints. Do we expect D to be close to SA? No way, right? So D is going to be super small compared to SA. So this is over constrained. So what can we do? You have an over constrained linear system, maybe infeasible. You have too many constraints. There is no solution. It's almost guaranteed there is no solution to it. Also, we don't have T of pi, right? Like we just have data. But maybe that's not a big problem because the data can be used to effectively as if you had T of pi. It's like for every of the state action pairs that you have in your data, like you see at least one next state and one reward. And if I write out this this TD equation here for a specific SA pair, then it's going to look like this. Out of E. Okay. I just write this. Okay. So this is taking a big average over this function, right? And you have this SA pair in the data. Well, of course, you don't have this whole big vector of probabilities, but you have one data point there. And so you have basically access to this guy. At some S prime. Okay, so you have SI, AI, everything is I, indexed by I, so that it's clear that this is like one data point. And so now we have this data, and okay, maybe scratch this. This is just RI. You don't have the actual reward, but like you have an unbiased estimate of it. And this lengthy thing, if you evaluate it at a fixed state, it's something super simple. It is just you have phi at SI prime, and then let's say for the sake of simplicity that this policy is deterministic, so that we don't have to write averages over the actions. Then this is the equation. Oh, sorry, like there is a theta here. This is just what you got, right? And so the expected value of this conditioned on SI AI is exactly this. So you have unbiased estimates of the right-hand side of these equations. So maybe it's not a big deal that you don't have everything. And so TD just says that, well, these guys add the data. So I like to call this the delta I of theta. Well, okay, we'll see what that is going to be. So this is just like the TD error. And wishful thinking, this should be all 0. And so from here, you could say two things. Well, maybe you want to square this. And that's really dubious. So some people would go there and then would say that, well, let's just minimize this. Because we want a loss function. It's a natural human instinct that you want a loss function. So what is the problem here? The problem is that this introduces some bias. And the reason for that is because you have stochastic transitions. If you didn't have stochastic transitions, then there would be no bias, there would be no problem. But even in the limit of infinite data, if you have stochastic transitions and you have realizability in everything, the minimum of this loss may not give you the true solution. So that's not nice. Like, no consistency holds. So the problem is, this is a big problem. I mean, like, big problem, I don't know. No consistency. This even fails the very first test that you might think about, that, well, in the limit of infinite data, if I have infinite compute and everything is so nice that Q pi is linearly realizable, is this guaranteed on every such circumstances give me a parameter vector that realizes this Q pi? The answer is no. Okay, so that's a problem. And so the other thing that people do is that you can correlate this with your features and some other functions of the features as well, if you wish. And then you sum it up. I don't know, dividing by n is not, it's completely optional. And then you just say that, well, let's just solve for the value of theta that gives me 0 here. Okay. So this says that the TD errors correlated with the features should give me 0 error. And so this procedure is called LSTD. And you can view it as trying to solve the fixed point equation in this smaller space and doing that in a, I don't know, somewhat arbitrary manner. So this is not based on, like any statistical design that would tell us that this is the best choice. Actually, a lot of times this doesn't give you very good solutions. So the errors that in the limit of infinite data you can read out, like the error of theta, can be like pretty large if you are in the unrealizable case. So the blow-up factors can be totally uncontrolled for many reasons. But this is one way of going about things. You can certainly try to do this. There is a lot of other procedures that people also suggested. And there is also statistical analysis, like discovering sufficient conditions under which any of these procedures work has been done. Like there's been a lot of work on this. And maybe the remaining work for this is to complete the analysis by saying which of these conditions are really necessary or which could be lifted. I suspect that pretty much all the conditions that we tend to have in this analysis are going to be necessary, in the sense that if you remove any of these conditions, then all bets are off. Like there, you can construct an example where the errors are not going to be under control. So the next idea could be that, so we still want to solve this fixed point equation. Q pi is equal to T of pi Q pi. And you can try to iterate. So you have data that gives you an unbiased estimate for T pi applied to Q. So call that operator that does that T hat of pi. So you can come up with a procedure that just iterates this. So this is least squares fitting. So this operator is defined such that, well, there is this data, right? So this is my target for some given theta to give me the next theta, right? Like I'm not going directly for solving the fixed point equation. I'm using successive approximations to solve the fixed point equation. And again, you can analyze this. This tends to require a condition which is called the closeness condition. That means that if you start with functions which are linear and you apply this T pi operator to these functions, then you get linear functions or something close. If that is the case, if you get exactly linear functions, so that would be a strong condition. And we mentioned linear MDPs. In linear MDPs, this is what would happen, right? Like in linear MDPs, you apply the transition kernel to anything, and then you get something that is a function of the features. So in linear MDPs, this would be satisfied. And then you're really lucky, because then you can do this iteration. And I bet maybe in that case, you can directly solve for the fixed point too. I'm not completely sure about that. And then all the errors are going to be under control. And then once you do all of this work, eventually you derive an L infinity error bound on Q pi, and you can plug into the error bounds that were completely general, independent of how you are estimating the action value functions. And the previous calculations that we were doing for the planning case apply. Okay, so the difference between the planning case and the batch case, as far as all these algorithms are concerned, which are based on estimating action value functions, is that in the planning case, we had a much easier job in producing these action value function estimates than in the batch case. So in the batch case, we have all these ideas floating around. None of it is really truly great, but But this is what people are using both in practice. I mean, like you can do this with neural networks, and like any of these procedures can be written as some loss that you're minimizing, and then you can replace the linear stuff with a neural network if you wish. Yeah. So one must wonder about whether there is anything that we are missing here. Something that would, when it comes to using the data to come up with a good policy, like, okay, we kind of drifted off, and then we said that we are gonna focus on this policy iteration type of algorithms, which naturally come up with policies, and then you need to avoid the policy. So that's one way. The other way would be the value iteration way, where you would need to approximate the Bellman optimality operator, and you can do that too. Again, some closeness assumption regarding the function spaces is going to be brought in. And you can run all these analyses, and then you can get error bounds. You can get sufficient conditions for the errors to be under control. And every once in a while, so there are two things that come up, this closeness. And then here I was sweeping under the rug that, like, because somehow there are this divergence happening with the trajectories. If this divergence didn't happen, these density ratios would be under control, then everything would be nice. So if you suddenly assume that magically these quantities are under control, then you can again get good error bounds, of course, because then you can just run, the usual analysis. All these guys are bounded by a fixed quantity. That quantity is going to multiply the approximation error at the end. Like if you plug it into the polydeck bounds, just multiplies the approximation error. It also multiplies the estimation error, but a big deal. Actually, the approximation error doesn't get multiplied by it. I think the estimation error, you can work it so that like just the estimation error gets multiplied by it. If it's a bounded quantity, you're done. And that's a lot of times what the analysis, the various analyses are doing. Okay. So two things seem to be coming up a lot. So maybe if you can control the density ratios, or you have some sort of completeness of the function space, then you can push through the analysis with some effort. It's usually a lot of calculation. And you can have a lot of fun too. Sometimes people bring up this issue that whether you have IID or Markov assumption. So if you have a trajectory, then the trajectories maybe, like maybe you have multiple trajectories, maybe they're independent of each other, but maybe you only have one trajectory. And along the trajectory, you have these correlated state action pairs, right? Like if you're in some state action pair, like that, this is your Z space. You make a random transition to the next one, make a random transition to the next one. you're going to be local, governed by the kernel induced by the interconnection of the policy and the Markov transition kernel of the underlying MDP, right? So that makes these little steps. And here, consecutive data points are not independent of each other. They are correlated. But the Markov assumption still there. It can save you. If you throw in mixing, then there is an analysis that goes back to Bernstein. It's like the turn of it's a 1906 kind of type of result. That's like 2 centuries ago. Now we would say that, or just one. I don't know. It's like, okay, it's 100 years, more than 100 years ago. And he basically says that, okay, if you have a process, so mixing means forgetting the past. Or decoupling from past. So it just means that the distribution between a time point t and a time point far in the future, well, okay, I don't know, capital T time step later. So this distribution, the dependence of this distribution on the initialization here is weak. It's like forgetting it. Like it's not a strong dependence. So somehow the distributions converge fast to some underlying distribution. Usually, if you have, for example, finite Markov chains, it's always geometric convergence if you have convergence at all. And if you don't have convergence, then maybe you do some additional averaging, and then you always end up with some convergent behavior. It could be nasty, but like if you had convergence, it's going to be a geometric convergence. So forgetting the past geometrically fast. And because of that, you can play this game when you have your data, and then you create blocks in the data. And so having a big T means that the distribution here that you see is almost independent of what you have seen there, right? So if you start to condition on data here, it almost doesn't matter in terms of the distribution observed here and later, okay? So that's approximate independence. So that's another way of like that independence comes back. So you create these blocks in your long trajectory that has a length of n, and each block is going to have t data points in it. And then just like mimic that, you cancel every second one. So you only keep the ones with an odd index. And then you remove all the other data. And then within this data, you're not going to use the independence. You just say that like, oh, that's my data block. That's just like one data block. And then this data block is almost independent of this data block and almost independent of all of this. So you're kind of like reducing everything to the IID case. So this is called a blocking technique. And with this technique, you can analyze data generated by following Markov processes, and the results are going to be similar to what you had, except that the amount of data is reduced by a factor of roughly t, which is your mixing time. And in the procedures, like you can be more clever. You don't actually have to cancel anything. You just do the cancellation in the analysis. So you analyze things on the odd blocks and the even blocks, and like it has some technique to it. And altogether, if you had a rate that was a function of n, no, that is going to be a function of n over t. So as if like you had t times less data points. Should be quite intuitive. So if you have bounded mixing time, then all is fine. And this correlated data shouldn't bother people too much. Once you learn this technique of bursting, of how to use this is called the independent blocks technique, then you can prove everything for that. So that's really nice. All right, I will stop here. This next time I'm going to talk about whether we can remove any of these really inconvenient. Oh, there was another assumption that we kind of suggested that, well, we should have at least for extrapolation error control, we should have, you know, like this minimum eigenvalues like bounded from below by an absolute constant, or like things are gonna go bad. If you have a good design, like optimal experimental design, then this value would be 1 over d. 1 over d squared, so that just means that, oh, the extrapolation error is not like square root d times the approximation error, but d times the approximation error, and so on and so forth. So this minimum eigenvalue is really the quantitative watch if you want to control extrapolation errors. And so the question is going to be, are these really necessary to get good results? And the answer will be presented next time. All right. I will provide pointers. There are lots of papers about this. Okay. See you guys.